Hello, my name is Mark Silver, and I want to show you what it sounds like. I guess we're going to listen to what it sounds like when we're using UHF radios with RTK equipment. The first thing I want to mention is if you're using a high power repeater, that's a radio at a power higher than a couple of watts, you want the antenna to be above your head. We need to treat 35 watt repeaters at 400 megahertz with a little bit of respect because they can hurt us. The next thing is when you're working in the field with UHF radios, you always want to have a handheld radio. Now, I have a Baofeng UV5R. These are about $25 from Amazon. And I'll just tell you, the first time you really need one of these radios, it'll be the best $25 you've ever spent. So let me show you how to use this radio to start off with. When you turn it on, you want to push the orange button
Channel mode
until it says
frequency mode.
And then we're going to type in the frequency that we're interested in working with.
4610255.
And you'll hear that there's, in this case, there's someone else in our neighborhood on the frequency that I dialed in. All of the licensed frequencies that I'm legally allowed to broadcast on will have somebody on them already. We're in the middle of Salt Lake City. None of the other users will be licensed users. So that brings up the next point, which is if you're using a UHF radio, an FCC license is required. I'll leave a link down below to an article I wrote on pirate surveyors. I'll just say, I don't care whether you have an FCC license or not. However, if you ever get caught transmitting without one, the fine is $10,000 a day. So there's probably a 0 chance that you get caught, but if you ever do, you'll really, really, really wish that you didn't do it. Now, this is going to be an interesting video. I'm not going to turn on receivers live, but I have videotaped different configurations. So the first thing I want to play for you, a short snippet from a radio. That snippet is a radio broadcasting my FCC ID. When you get an FCC license, you will get a call sign, and you can program that call sign into a legal radio, and once every 10 or 15 minutes, it will broadcast your FCC in Morse code. So what we just listened to was dit da da. See, I've got these annotated up here at the top, which is a W, and then da da dit da, which is a Q, DN367. That's my call sign. When you're listening on the radio, you'll hear this call sign, and it takes, 3-4 seconds to broadcast. While the call sign is broadcasting, neither your base or your repeater can send corrections. And so you'll see the latency on your rover go from 0 or 1. Momentarily it'll go up to 4 or 5 seconds and then pop back down to 0 or 1. Next, let's talk about the amount of time it takes to broadcast a correction every second. In our user manual, we ask you if you're using a repeater to broadcast in SCMRX, that's scrambled CMRX. And the reason is CMRX is a compressed, compact protocol. So the length of time it takes to broadcast one correction is shorter than with RTCM 3.2. So I've got some other snippets here. This is RTCM 3.2 MSM with a 0 degree elevation mask. So I've taken a screenshot of the waveform, and you'll see here's the burst of energy that you heard, and then 1 second later there's another burst of energy. The problem with RTCM3 is that one correction lasts 567 milliseconds, more or less. If there's more satellites, this will be longer. If there's fewer satellites, it'll be shorter. But at 567, there's not enough time in 1 second for it to be broadcast out of the radio and then repeated and broadcast again by the repeater. So, what we heard at the beginning, those messages were longer than half a second, and the two radios are talking at the same time. So for this set of two corrections, there's no possible way for the rover to receive a message because the repeater is talking on top of the beginning of the second message from the base. Now when we come over here, that's what we would like it to sound like. So you hear the primary message, followed by the repeated message, followed by an empty space. We can also make the length of the message shorter by raising the elevation mask in RTCM 3.2. Let me show you that. So in this example, we're back to RTCM 3.2 MSM, but I have raised the elevation mask on the base to 15 degrees. That should give us enough time to broadcast the original message from the base and then broadcast the repeater's message. So you heard there that there's enough time for both messages to be broadcast, the first message from the base, and then the repeater repeats the same message, and there's a little bit of time left over before the next second, and then the next message is broadcast. This is pretty close. So in this particular case, with a 15-degree elevation mask on the base, the transmission is 487 milliseconds long, and you'll see there's enough time in here before the next second starts for the repeater to broadcast the more powerful second message. Now let's listen to CMRX. 32 satellites. Because the message is shorter, there's more time for the repeated signal to be broadcast by the repeater. So in this case, the base is transmitting first, and then immediately afterwards, the repeater is repeating the same message again. And then there's enough time before the next second starts to ensure that the base, when it starts transmitting the second message, isn't overwritten essentially by the repeater. So here we are with scrambled CMRX tracking 32 satellites with a 0-degree mask. Because the message is more compact and compressed, it only takes 440 milliseconds for the message to be transmitted. There's plenty of time in the rest of the second for the repeater to get its message out before the base transmits the next sequence. Now there's other options for broadcast correction types. There's RTCM, which is RTCM 2.0. That only transports corrections for GPS. So if you use RTCM 2, you won't be able to use GLONASS or Galileo BeiDou L2C, L5, or GLONASS L3 on the rover because there's no way to transfer those corrections in RTCM 2. There's another protocol called CMR, is a compressed RTCM 2, so only GPS satellites are involved in CMR. The next protocol is CMR Plus. CMR Plus can also include corrections typically for GLONASS. So if you choose CMR Plus, you'll get GPS plus GLONASS, but you probably won't get L2C, L5, GLONASS L3, and you definitely won't get 3 Galileo satellites It's missing correctors for L2C and L5. Then there's RTCM 3.2 MSM, which includes correctors for everything, but is very long, as we've seen. And then the final is SCMRX, which is scrambled CMRX. Now on a true Trimble receiver, an R8, an R10, an R12, you're going to have CMRX, which is not scrambled. So SCMRX and CMRX are essentially the same correction schema, only the scrambled has been scrambled so that you can't intermix Trimble receivers with receivers that use Trimble OEM boards. One other thing that I would like to discuss is how do you choose the broadcast protocol. In SurfCE, when you click on Equipment and then GPS Base, go to the RTK tab. The message type is in this drop-down box. And you'll see there's a lot of messages. There's CMR, CMR+, SCMR, RTCM V2 2.3, RTCM 3.0, 3.1, and 3.2. If you're using a repeater, you definitely want to choose the protocol SCMR. It's worth noting that SCMR and SCMRX are identical protocols. It's just a naming convention. So in more Trimble-esque environments, it'll be listed as scrambled CMRX or SCMRX. And in some Carlson environments, the message type is listed as SCMR. These two message types are identical. There's no difference between them. So, once again, you've made it to the end of an incredibly boring video. If you have any comments or questions, you can leave them down below and hopefully I'll find them and answer them. If you're interested in RTK or UHF modems for surveying, you can click on the subscribe button down below, and when I do new videos, you'll get a notification from YouTube. Thank you very much for sticking through to the end of this video. Have a great day.